have detected gravitational waves. We did it.
Okay. So why didn't you people clap? Because that was a moment. So, in the last year, 2015, that was the centenary of Einstein's general theory of relativity, unprecedented, unique theory, never given before, purely logical, and maybe never be repeated again, and that was the last 2015. But this year, 2016 again, now here is Einstein, that is the equation is the general theory of relativity equation. You see R, I, K subscript equal to 0. It looks simple, but it contains within that, like a pen drive contains so many videos and so on. It contains 10 non-linear coupled differential equations, almost impossible to solve. Even Einstein thought it would never be solved, but it was solved within a few months. I will come to that a little later. But in 2016, Einstein himself, working on his own general theory of relativity, he was an incredible man. Nobody has appeared on this world. Two people were right together are Newton and Einstein, and nobody can come near anywhere. Okay, so he himself worked on that and predicted that there should be gravitational waves. He had already given space-time, how space-time curves because of gravitation and all that, and the ripples that are going. Why am I doing all that? Probably you can't see me at all. Now, ripples that go are known as gravitational waves. You will have to ask somebody to give an hour-long lecture about gravitational waves. But tell you very simply, see, for example, sound wave comes because of the vibration of larynx and so on and so forth. And electromagnetic waves come because the electrons jump around in the heated filaments and so on. And the gravitational waves comes simply by the motion of particles or objects. So when I do this, gravitational radiation is coming and hitting you. If it was electromagnetic waves, the other electron would also be jumping around by resonance. So, but the gravitational waves are so weak, you won't be doing what I am doing. Otherwise it would have been terrible. If the teacher is writing, you would also be writing something else. So somebody is dancing, the people will also be dancing. No, you can do it voluntarily, but not involuntarily. So it is very weak. So people realize if you have to observe gravitational waves on Earth, it has to be from something that's happening up there in the sky with huge objects, where the black holes come. Okay, huge, very massive objects. Only when that happens, the energy that is received on the Earth should be high enough that you can detect them. So it was all known, but how do you do this? Next slide, please. And before I come to gravitational radiation, let me talk about black holes. Einstein thought his equations would never be ever be solved. He was very depressed about that. But within a few months, Carl Schwarzschild was a brilliant astronomer and a theoretician, quantum theorist, electromagnetic theory and so on. He studied general relativity and gave the first solution, the simplest spherically symmetrical solution, and he didn't know that, but built into that was a spherically symmetric black hole, now we call Schwarzschild black hole. That came to be known much later, and I was very fortunate enough to work on Schwarzschild black hole for my thesis. Here it becomes a little autobiographical, I hope you don't mind. So for my thesis, I first studied the structure of black holes, both spherical and rotating. I will talk about that in a minute. And also I proved the stability of black holes. If there is no stability, there is no existence. Only if you are stable, you can have a stable existence. For example, Humpty Dumpty sits on the wall. It's an equilibrium state, but you nudge him, he falls. So that's not stable, and all the king's men and all the MES college people could not put Humpty Dumpty together again. So he won't exist. That's my second thesis, not on Humpty Dumpty, but on black hole stability. And I will come to the third paper, and fortunately you have read about it in the newspapers. So I don't know, fortunate or unfortunate, they give you wrong things. So I'm going to give you the right thing, okay? So don't say I gave the wrong thing and the papers gave me. So Schwarzschild gave, and the structure, next one, as you can see, you can't see the black hole. It is there. The black is there. And the spherical surface is known as the event horizon. So why things go in and cannot come out? Okay. So this was my first paper where I mathematically proved why things can go in and cannot come out. And also the structure of the black hole and all that in the first paper. And the second paper was stability. So at the center is a singularity. If anything goes in, it will be completely crushed out of existence. So one shouldn't fall into the black hole. That's the model. And the next one, next please. How do black holes arise? For example, this is the stellar evolution. There are a lot of clouds, gas clouds in the universe, in the Milky Way and so on. So they condense and then becomes a red giant, and there is a planetary nebula, and finally it becomes white dwarf. Chandrasekhar's greatest work when he was only 20 was to derive the great Chandrasekhar limit. So beyond that there won't be any white dwarf. So Eddington was a very venerated man, openly made fun of Chandrasekhar. What would happen to another big one? Will it go on radiating and all that? Chandrasekhar was crestfallen, and he went to the Commons and said, this is how the world ends, not with a bang but with a whimper. That is T.S. Eliot's words, sentences. And he left Cambridge and went to Chicago. So at that time nobody ever thought of black holes. Black holes came only in the 60s, but Chandrasekhar limit was a great thing from which neutron stars and neutron star limits were derived by Oppenheimer, and then the limit for beyond that they said black hole will occur. No force in nature can stop gravitational collapse and all that. That came only in the 60s, okay. But Chandrasekhar, and also Chandrasekhar worked on so many things, radiations transferred and stability of hydromagnetic fluid, rotation of fluids and so on. Only towards the end, the 10 years of his life, he worked on black holes and wrote a big book on that. And we became very good friends, academicians, of course. He was Chandrasekhar up there and I here, but still. And I will refer to you someday, send Balchandra or Professor Iyengar, an article I wrote, very non-technical. It's called Leaves from an Unwritten Diary, Reminiscences of Chandrasekhar, and where I give our mutual interaction. And it gives a wonderful, not because I wrote it, there is a portrait of the man. Anyway, I'm sorry, I'm going away. But on the other hand, a heavier mass star goes through these various phases. It can become either a neutron star if it is heavier than 2-3 solar masses, the core will become a black hole. That is how it is produced. So there must be millions of black holes floating around in our own galaxy. So there are black holes. Now the next thing is you have one ingredient, black holes, and the next ingredient is the gravitational radiation. Next slide. Oh, sorry, before that, I'm sure you can identify one on the right. 2004, which means 12 years younger. The clock cannot be reversed. I have more dark hair. But this gentleman, his name is Roy Kerr from New Zealand. He was visiting Bangalore, and in the planetarium I am showing some experiment of levitation. And I told him this is very old, probably Balchandra can tell you about it. In the Vedic period, they could, by their own spiritual power, they could levitate. That doesn't happen. Okay, so I was showing it to him. Kerr was the first one to show that there are rotating black holes. Next one shows you the structure of, this is what I did for my thesis, the first paper. There is outside, there is one surface, and the event horizon is inside. Things fall in but cannot come out. It's a beautiful structure and beautiful physics and all that. So we have therefore these black holes. Most of the, all black holes probably are rotating black holes, because everything rotates. Electron rotates, Earth rotates, galaxy rotates, even department heads rotate. So everything rotates, so black holes can also rotate.
They are rotated, sir.
Next one, let's see what is. And this is, whenever you have a black hole, things fall inside and produce this accretion disk from which plasma comes out and you can see and all that. But the most important is the source there, that is the black hole itself. So this we are not concerned, but that's also beautiful. Physics goes on there, plasma and everything. So next one. This is again, inside every galaxy, there is huge, there are solar mass black holes, but inside every galaxy they have found there is a super giant black hole. Within the Milky Way itself, there is a black hole sitting there which is 3 billion solar masses. Sorry, 3 million, 3 million. But the highest is about 3 billion in another galaxy, but 3 million is also very large. And many things happen. So hyper whatever, connect with the next one. So here is a binary one, and it's going out and sucking in matter. So from the source, can you get the sound also?
I have the WAV file.
Yeah. This is the, when he is saying our, my guru, Dr. H.N., he said some speaker asked the organizers, how long can I speak? So the organizer said, sir, for a person of your erudition and standing and status, how can we put a time limit? You can speak on as long as you want, but remember, we will all be going away after 45 minutes. So anyway, what I am going to tell you is, if you see this video, you will see first of all the binary of the two, and then the next one would be the galactic, inside our, as I told you, Milky Way, there is a huge black hole and matter falling in and all that. When they are doing it, let me continue. Now, we go to the gravitational waves, as I told you, Einstein himself predicted the gravitational waves, and can we do one thing? I will show them just the slides, and then we will try to play all the videos one after another. Okay? So let's go to the slides themselves. Yeah, gravitation. Go to the next slide. Next slide. Yeah, Albert Einstein. So he wrote the gravitational wave equation and also gave the formula how if things move, gravitational waves should be produced. Although he gave the theory, next you click. He was this is if you go the gravitational wave goes. This is the polarization. Instead of going round, it will be going like that. Next, click next. So he himself was skeptical about the existence, but then he realized, go next, that it exists. Yes, they exist. So next slide please. And when I was a graduate student in the University of Maryland doing my PhD, we had the senior most professor there, Professor Joseph Weber, and he was the pioneer in trying to find out the gravitational radiation coming from outside. And the next one shows his equipment. It was a huge bar, and he said if the gravitational radiation comes and hits it, there would be minute vibration almost of atomic or nuclear size, and the transducers there should detect them. But unfortunately, he thought he had detected them. But then people said it cannot be reproduced by others, so he had not found and so on. He was very sad. But he was an inspiration. And what today LIGO, that is a laser interferometer gravitational waves observatory, is supposed to have seen the very first one where the video worked, and they announced that the pioneering thing he did was the inspiration to them. So the next slide. Now this is LIGO. There is 4 kilometer arms there, pure vacuum in which the laser has to go, reflection occurs, and they see the interferometer fringes and so on. I don't want to go to the technical details, for the very simple reason I don't know that. Okay? Don't tell anybody. Now next one. Right. What did this comes from, after they did this, announced it, they published a paper in Physical Review Letters, and it is taken from this. And to give them due credit, in the paper first they give Einstein, first 2 papers, and then Schwarzschild, whose black hole I showed, and Kerr, whose black hole I showed, and then next, modesty doesn't permit me to tell you whose they give, no need to plan. They give reference to the paper I wrote in 1970, and in the PRN they tell you what they observed. What they were observed was 2 black holes, quite massive, about 20, 30 or something like that, going round, waltzing around each other, attracted just like a planet going round like that, but giving out gravitational waves, coming closer and closer. So when they do that, the frequency keeps going up, and also the amplitude goes up. This is called chirp, like a bird chirping. I don't want to make that sound. And they did that when they were showing it. Quick, they said, okay, that's called chirp. No, previous one please. I'm not done yet. Okay. When they merged, there was this black hole on the right hand side that became static. No more dynamics. then how do you detect there is a static black hole doing nothing? Then came the last thing there, and those are called quasi-normal modes. The last part. And looking at them and measuring them, you can tell the mass and the angular momentum of that. And this appeared in the 1970 paper. I was a postdoc 1 year later than my PhD thesis. Fortunately, they gave me PhD, and I was a postdoc, and I wrote that because in the first two papers, I had done the structure of black holes, stability of black holes. The obvious question to be asked is, how do you see the black holes? So for example, how do you see everything because of scattered light? And how did the great Rutherford see the nucleus scattering alpha particles? So I said, how do I was not comparing myself with Rutherford, heaven forbid. So I said, how do you see the black hole? Send a gravitational pulse and see what happens. So I made the gravitational pulse going, it's a Gaussian, the mathematics student should know, like this. Made it thinner and thinner and thinner and lower and lower. You know, the computers were very poor in those days. In the evening you had to give a stack of punched cards and go in the morning and look at the output. So if the Gaussian was very broad, it's like a huge wave washing over the stone. Nothing happened. And made it thinner and thinner, then out came the quasi-normal modes. That's what you see at the end. So my colleague Mr. Mansuna has created what happened with my experiment, a computer experiment, that he has given a visual one. Next one, please. So in goes the Gaussian. There is a black hole which you don't see. Out comes the quasi-normal modes now. See? It should go to the right. It's not going. No, it's stopped. There's the black hole. Can you see the black hole? Yes. Yeah, this made us see the black hole. So this is the recreation he made of what I got. Next one, please. This is, you see, this is from the paper. But if you had done that on a more powerful, even on a PC, you would have got much more. And this is what they got in LIGO, actually the one they got at the end. This was the signal which was all garbled, but they processed it, and this is what they got. Observed LIGO, and this is predicted in 1970.
Congratulations.
In the old days, we used to clap often if we wanted the speaker to stop putting that. Is this what you are doing? Okay, thank you. So this is the comparison. And so that's why when they wrote, and then there was a lot of, people wrote, and hopefully it will be accepted. It is accepted because the PRL paper gives complete reference and so on. So next one, I don't know what it is. Can we go to, huh? Okay, this also sound.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in the system was in the form of gravitational waves, ripples in the very fabric of space and time.
At the end,
These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
Replay, please.
So you can stop it there. And so this is the story, and as somebody kindly said, that for LIGO itself, they worked for 30 years to achieve the sensitivity. First, they had LIGO, then improved LIGO, then advanced LIGO, and they could find it. And they found it in September, and they announced it on 11th February, and there were some reasons for that. Let us not go into that. And somebody kindly said that with the LIGO's finding detection of the gravitational waves, not only Einstein was verified, but the 1970 prediction was also verified. So they all. So somebody said that I have been waiting for 45 years. I have not been waiting. When I wrote that paper, I thought it was all purely theoretical, because at that time black holes belonged to mythology. Gravitational waves also belong to mythology. Believe it or not, when I was doing this, some of my friends said, "You have gone insane trying to do this." But anyway, as I said, I have waited 45 years. I have not waited 45 years. I have waited 1.3 billion years. Because that's what So I have told you the story, and it's not the end, because the LIGO is going to work more and more. Hopefully it will find more of gravitational waves, and let there be light, as Newton, God said, let there, what is that? And Newton, okay. So thank you very much for listening.
To come over on the stage.
Can you take a few questions?
Yeah.
As I always say, you can ask questions. I don't guarantee I will answer. Okay, go ahead. What's the question? Where is the question?
My question is that with your considerable experience in this and this discovery having come, what do you see as the future of
research and collaborative research? And what role will Indian institutions, the Pune institution that you referred to, play in the endeavors of the course?
Okay. One first thing is what will all this gravitational wave detection do? Is for example, it opens a new window in the sense many events like this black holes colliding and all that may not be amenable to optical observations. Huge amounts are done in optical, but certain things may not be, and the gravitational waves will do that. The most important thing in the gravitational wave detection is this. In the early universe, when the Big Bang occurred, by the way, you know, there was a Fred Hoyle and Bondi and Tommy Gold. They gave the steady state theory, which did not hold water because because of the background radiation, they could not explain. But at the time when both were viable, Hoyle denigrated the other model, saying, "Oh, singularity, Big Bang," he said. But he said it in a denigrating manner. But it caught on. So now we say Big Bang, okay. And so when the Big Bang occurred, immediately the universe was filled with plasma. And light does not go through plasma. Only when it expanded and galaxies came into existence, then optically you can see that. But what was happening in the early universe when light could not escape, only gravity waves that come through can tell you. So when gravity wave detectors become so sophisticated as optical ones, it will tell you what was happening right in the moment, after a millisecond or microsecond after the Big Bang. That's very important for research. Now, the Indian component. There are two people, Professor Bala Iyer, and here in Bangalore at Raman Research Institute. Professor Iyer, I was in Raman Research Institute for 76 to 92. For 12 years, Professor Bala Iyer worked with me. I take pride in that, and we wrote 12 papers together. And Sanjeev Durandar, who is an IUCA, he worked with me for 2 years and we wrote 7 papers. So these are all, younger generation with whom I was very happy to work with. But then they went on to gravitational radiation and they did lot of theoretical calculations. And if you look at the PRL paper, there are 1,000 co-authors, and out of which 35 in India and about another 15 or so Indian origin people outside the country. They all put in the theoretical things, and also some of them worked on the LIGO hardware also. So that they were all not working for 30 years. For at least 15 to 20 years they have been feeding all the theoretical things for this going round, merging at that stage and all that. One is production of gravitational waves, Bala Iyer was doing, and Durandar was doing how to look at it. It's very sophisticated because you have to build what they call templates. What you get is garbled. But only if you put a template and filter, then you will see what you are looking for. It's like filter is like making tea. When you make tea, which I love tea and I make it myself, you put the tea powder and all that, what you get is completely garbled because tea powder is there and pure decoction is there. Only when you filter it, the tea powder which you don't need, tea leaves, that's like the noise, that goes away. And the decoction which you want to drink, that's after the filter, what you need like quasi-normal modes, you get that. So Sanjeev Durandar was building templates. So Balayar, my old colleague, was generating gravitational radiation, and Durandar was building templates to see them. I used to ask them, why did you have to spend $1 billion to build LIGO? Between the you two, you generate and he observes. Why 8 billion? By the way, the $1 billion were given from National Science Foundation by my colleague. He and I worked together with Charles Missner. His name is Richard Isaacson. He was the one who gave. And in the first one, when they announced, he is sitting right in the front second row with a shiny bald head. And he wrote to me, Vishu, you please look at that. I am illuminate LIGO with my bald head. So we have to, one great thing that happened to me was, so many of my old friends wrote to me. We became close once again. So now, I haven't answered the question, sorry. So now they want to bring, this is Indigo, they want to bring the LIGO from US to here. So America is ready to give a clone of what they have. We are not going to give that, but the exact replica of that to India, so that it will cost 1,260 crore rupees. Many scams, so global more than that, so it's all right. But it will take a long time. So you need younger generation. Maybe they are not born yet, but they will have to be trained, hardware, software, hardwares and so on. So they are all working on that. And in that Balayar and Durandar, Ajit Kandavi, they are all, they agree that they are all my bache. Okay, they are all working and hopefully it will work someday.
Sir, do you see any practical applications in day-to-day life?
This is a question which is asked always, and yesterday in the press conference also it was answered. There are two answers to that. When Faraday found electricity, somebody, I think it was Faraday, I don't know, Disraeli or somebody asked what's the use of this. He said, sir, someday you will be able to tax it. So today, KEB or whatever, they charge us, right? And they give you these bulbs, LED, so that the consumption goes down. So, that is one. Another thing is, whenever you have technology, space technology, what's the use of that? Every technology has a spin-off. They manufacture things, they create things that they come into everyday use. So you ask the space scientists, they will rattle off so many things that has percolated into our daily life. I don't know those things, I'm sure there are a lot of things. Even space, NASA said the epoxy they had to create became extremely popular, used super glue and all that, okay? And Einstein, supreme example. When Einstein gave his theory of general relativity, purely theoretical, what's the use? But your GPS uses general relativistic correction. If you use GPS and wanted to come to MES college, if there were no GPS correction, you would have ended up in Central College. And you wouldn't have been able to, or in the pub somewhere. You would have had a nicer time in a pub than in MES. Okay, now that is one. And then somebody asked black hole research about the galaxies, universe expanding. Somebody asked Chandrasekhar, what is the use for the human beings, humans? So Chandrasekhar gave the most profound answer. It helps the humans to remain human, to have this feeling. How are we human? Because of our curiosity, the inspiration. Why do you enjoy poetry? Why do you enjoy music? We won't spend that much money. We may have to spend that much money to keep, the inspiration and the drive kindled. Remember that. And we are human. That's the other one. Okay?
So, one small question. Since we are in the college atmosphere, how was your student days, and were you a hard-working student or an intelligent student?
You want me to confess? I will confess with a little boasting. Okay. What happened was, all our education, I am taking too long, I don't know. You can all go away. I will talk. The great Shankaracharya went to Mahishmati. What century was that? 9th century or whatever. Looking for Mandana Mishra's house. Because he wanted to have a debate with the Mandana Mishra and Purva Mimamsa and Uttara Mimamsa and all that. And he asked me, how can I find some passerby? They said, very easy, Venerable sir. If you go there, even the parrots in front were hanging from Mandana Mishra's house will be reciting the Veda. Beautiful. Works for Veda does not work for science. You can't learn science by rote as you learn Veda and then repeat it. But that's what we are made to do in science education. I got 3 gold medals in BSc Honours. I'm ready. Wait, don't. This is something you should not, really, I'm serious. I'm ready to throw away those gold medals because everything I wrote and one was by rote. I did not, one of the questions that was asked, derive Stokes' law. Eta, 6 pi eta, whatever. I had memorized it so that I could write it in 20 minutes flat. World record broken, and I did not understand a single step I had memorized. When I went to Columbia University, I went there thinking I knew everything. First day I was demolished because my professor said, solve this problem, assignment. Everybody solved, I didn't know how to solve. Why? Because I had been trained to memorize and write well. So, fortunately, and when I went to PUC or intermediate, Dr. H.N. I used to play table tennis and H.N. used to come and that's how we used to say, Vishveshwara ಮನೆಗೆ ಹೋಗಪ್ಪ ನೀನು. ಮನೆಗೆ ಹೋಗ್ಬೋದು ನೀನು ಚೆನ್ನಾಗಿ, ನಿನಗೆ 75% ಬಂದುಬಿಟ್ರೆ ಎಂಜಿನಿಯರಿಂಗ್ ಕೊಟ್ಟು ಹೋಗ್ಬಿಡ್ಬೋದು ನೀನು. ಹೋಗು. ಇರ್ಲಿ ಸರ್ ನಾ ಹೋಗ್ತೀನಿ. But I used to love learning mathematics and physics. I just learnt it not for exam. I learnt it for my pleasure. But lo and behold, one day I was very drowsy after food and I wanted to sleep. One of my friends, he came and said, H.N. has gone mad. You immediately come. I said, if he goes mad, let him go mad. I want to take my nap. He said, no, you have to come. And I said, he was really saying, ವಿದ್ಯಾರ್ಥಿ ಅಂದರೆ ಹೀಗೆ ಬೇಕಪ್ಪ, ಏನಾಯ್ತು ಸರ್? ಅನೌನ್ಸ್ ಆಗಿದೆಯಪ್ಪ ನಿನಗೆ 3rd ರ್ಯಾಂಕು, 95% ಬಂದು, ಇವಾಗೆಲ್ಲ 98.9997 decimal place, people take that, right? In those days, 95% was the record. So, ಈ ಥರ ಜಂಬ ಹೊಡ್ಕೊತಿದ್ದೀನಿ ಅಂತ ಅನ್ಕೋಬೇಡಿ, ಯಾಕೆಂದರೆ ಜಂಬ ಹೊಡ್ಕೋತಾ ಇದ್ದೀನಿ. ಅದು ಆ ಥರ ಆಗಿದ್ದರಿಂದ I was very happy. But I forgot that. So MSc ಎಲ್ಲ ತಿರುಗಿ ಊರು ಹೊಡೆಯೋದು. When I went to Columbia University, I realized we learn nothing unless you solve problems. That's why in the planetarium we have the what we call, it's a very structured educational program for children of primary and middle school. They come and play with science, with colors, with light. They make little gadgets, pinhole camera, little microscope. They are inspired. This is, I call this science education in early development. If you take the acronym, it says SEED. Then high school students come more structured, they solve problems, they do experiments. This is called science on weekends, SOW. So, and then BSc 3 years. First year they study again solve problems. Solve problems, otherwise you don't learn. Basics. Second year, and the teachers are all from premier institutions like RRI, IAA, ISC and so on. And second year more advanced. Third year with the same mentors, they do research problems and many of them write papers. This is called Research Education Advancement Program, REAP. So we have seed, sow, reap. So we have at the planetarium the tree of learning. So I do have hope students from MES college and all that, Bala Iyer and one Professor Lokanathan, legendary teacher, they used to teach religiously, even though Bala Iyer teaches there. So if anybody, students come there, and one other thing, somebody asked your question, MES college should take pride. You know why? 10 years ago or so, Bala Iyer took about 5-10 students from MES college, started teaching them, made them solve problems. That is why the idea germinated, and I said to Bala, let us do it in a big way. Started at the planetarium and it thrived and we have reaped. So it started all in MES college. Now we can.
Thank you, sir.
Understand you were saying. Now, Socrates said, the only thing I know is that I don't know anything. So if you start with a mathematician, I think it was Hamilton, his motto was, I do not know. Only when you accept that I don't know something, you will learn something. But many people say, I know everything. I will give you the ultimate word of wisdom. You will never ever learn. And one thing I tell you, I always tell the students, if you listen to us, Balchandra or Professor B. Vishveshwara, Vardham Nasima, what you should know is you didn't understand. You go back and try to learn that. So it's very important that we make you not understand certain things. Then you must go, but it's on your, it's your responsibility to go and learn. That's very important. The other thing is learning by rote. We had a legendary teacher, Professor B. Vishveshwara will tell you, he was his guru also. Subramaya, D.S. Subramaya. He used to go to him also, in stories he used to tell me about Professor Srikanthan. I won't tell you what stories he told me about him. Anyway, he once told that learning by rote, in one class, high school or college or whatever, I don't know where you learn. So one teacher started saying, he said, kinetic energy is half mv square. So he made the students repeat. Everybody said, kinetic energy is half mv square. So he made them repeat about half a dozen times. He was very happy. So everybody has learnt kinetic energy is half mv square. So when he was about to leave, one very meek student came and said, sir, I have a doubt, sir. Doubt? I taught you kinetic energy is half mv square. Yes, sir. But what about the other half, sir? So that's the note. I rest my case. Okay. Francis Bacon, you know, the great philosopher and everything, he says, you listen to this and think about it. Man was given imagination to compensate him for what he is not. And he was given sense of humor to console him for what he is. So he gives imagination to compensate. You are not this, you are not very handsome. So you imagine I am Shah Rukh Khan or Salman Khan. And then you say console him for what he is not. No, first one is compensate what and console him for what he is, what you are. And you say, well, I didn't have food, and then you laugh. See, for example, the great Niels Bohr, one Victor Weisskopf, who was there, he said, what is this in your Copenhagen Institute? Everybody is laughing, joking, pulling your legs, George Gam, all this. So Niels Bohr was very wise. He said, Victor, in our life, some problems are so serious, all we can do is laugh about it. So that's how we laugh. And it's very important that we laugh.